Okay. So if our u was this x, we want the derivative of u. That's kind of why I like you to kind of have these kitty corner from each other. So over here, we have u's and v's on top, and then our derivatives on the bottom. Some people don't necessarily do that. It doesn't matter. And then whatever your dv is, we want the antiderivative of that. That should have been sine of x. The formula then tells you to do u times v. So when we now go to set this problem up, the antiderivative of x times cosine of x should equal u times v. So here's your u, it's x. Our v is sine of x. Minus the integration of v du. So here's your v. And then our du, I should have written that out here. So v du. So our v was sine of x. Our du is just the dx. From there, pretty nice. The antiderivative of x cosine of x. This guy was ready to go. It's x sine of x. And then I'm going to treat this as a negative sign. So the antiderivative of a negative sign should be a positive cosine. And then plus our constant. And that's it. So right now, hopefully feeling pretty good about this. This isn't too bad. I would agree. Doesn't get too much crazier. But that's integration by parts. Now, number 3, we have not done this yet. And the reason we have not done this yet is because it requires integration by parts. Once we have done this, this is one that I would normally, when there's no calculator versions of quizzes and tests, fully expect you to get memorized. AP tests, since that they will monitor that. Make sure you get this memorized. This is one you're just going to want to have down pat. So this is, in fact, integration by parts, even though it doesn't necessarily look like it, because you're thinking, well, there's no product here. But there is a product all the time, right? Because we're doing a natural log times your dx. So there is a product there between the height of our bases, height of our rectangles, and then our bases. Well, here, this is not necessarily following our general rule, but you don't really have a lot of options, right? The only thing that makes sense is for our dv, the derivative of our v, or change in v, to be equivalent to our change in x. So those have to be our statement that dv is equal to dx. Well, that would then only leave one option for your u. Your u would have to be the natural log of x. Then hopefully we're understanding. We want the derivative of the u, so that's 1 over x dx. We want the antiderivative of the dv, so that's v, and then the antiderivative of a 1 dx would just be x. So now the antiderivative of the natural log of x should be u times v, so x ln of x, minus the integral of v du. So here's v multiplied by du, which is 1 over x dx. So in the future, again, you just want to get this memorized. We're going to get the antiderivative of ln of x to be x ln of x minus, notice how the x and 1 over x, the x's would cancel. So all we're really doing is the antiderivative of a 1. So that's x plus your constant. Okay. That will become commonplace now, especially in this chapter. You're going to see that often as we kind of move forward here. So you want to just kind of get that down. If you ever do forget it, then you got to remember it's integration by parts. That's the method we would use to go through that. Okay. All right. Number 4. So still thinking this is not bad. It's kind of fun. Not too hard. All right. So let's go to now number 4. Get that one set up. So see where we are at. Go through that first step. Go through that process. Get your u, get your dv, set up the integral, and see what we get. I guess I'll get you started on the first part. The x squared is the u, because if we follow that general rule, eventually you get 2x, then you get 2, and then you would get a 0. So that's the one whose derivative would eventually just go away. And then our dv would then have to be the dx, and then we still have the e to the x to take care of. All right, so now go through that process. And then my hope would be right about now, people are getting to something where you're raising an eyebrow and you're having this oh no moment. Now what do we do moment? And it's not that this is harder necessarily, but usually there's a collective moan when we talk about this and everybody's in here. All right, so let's see what we have. We're going to take our derivative. So hopefully we have this as 2x. And so that's du. And then the antiderivative of 1 dv would give us v. And then the antiderivative of e to the x is just itself. We then do u times v. So you should have started with x squared e to the x. And then we would do minus the integration of v du. So here's v, and then here's our u. So I'm going to rearrange it a little bit. I'm going to put the 2x first, so it's a little more appealing to the eye there, and then e to the x, and then dx. Then what I hope you recognize now is we have a problem right here. Because this is a product itself, we can't do the antiderivative of products by just looking at them. So that now either requires u substitution or integration by parts. So if you now look at this part right here, this is going to require more work. What we have is another product, and in this case, u substitution won't work. So we now have to do another integration by parts for that integral. That's where things get a little bit hairy and messy. So for this one now, and be very, very careful with your signs here. This x squared e to the x is all set. So he's just going to hang out for a while. He's ready to go. Then I have to do minus, and then we're going to set up another one of these, but whatever we get, we have a negative out in front of it. So I'm going to put a big bracket right here. And we have to set up another u dv for this other integral. Our u, we want to be that 2x. Our du is then 2dx. Oh, can't see that, can we? Shoot. Crap. People in the room can't see this. Let me make this a little smaller. Still better. You guys still can't see it, can you? Okay. Erase this. All right, so if you're at home, even if you're here, if you're understanding, go ahead and substitute those in. I'm gonna do this a little lower because it's not showing up on our screen in here. All right, so what can you guys see? Here's what I'm going to do. So I don't necessarily change yours, but let me get rid of this up here. And then I'm going to do a new substitution with this new integral. Why did that? Oh, I hate Cami so much. God, I hate Cami. Sorry, I couldn't find the Word document of this. I don't know where I have that in all my files, so I just made a quick PDF of it. And then it's a nightmare. All right, and then we had what? 2x e to the x. All right, so now we're going to set up another one of these. So we want our u to be the 2x, this guy, and then our dv to be e to the x. So the derivative of u is 2dx, and then the antiderivative of e to the x is once again an e to the x. You still can't see that, can you? Sorry. So now as we go to set this up, be very, very careful with your signs. So when I now go to set this up, this is where I left off, where we have this x squared e to the x is ready. But now when I do minus this integral, definitely use a bracket there, because whatever we now get out of this integration by parts problem, you're going to have to distribute that negative to everything. So we're going to do our uv. So this is 2x e to the x, using our new set of substitutions, minus another integral of v du. So that's 2 e to the x, and then our d to the x. So then as we now look at this, this should now be good news, because if I look at this integral, this we can do. That we know the antiderivative of. So the next step should be good. The next step should be our final answer. So the antiderivative of x squared e to the x is equal to x squared e to the x minus 2x e to the x. But then we have this negative getting distributed to this negative, so we would have plus, and then drop your 2 down. The antiderivative of e to the x is itself. Add your constant, and then that's our final answer. It is not a coincidence, so kind of keep this in mind. Notice how this was an x squared. It had a power of 2, and realize we had to do integration by parts 2 times. That's not a coincidence. So if we ever had an x cubed, then yes, that would probably mean we need to do it 3 times. Okay? All right. So just kind of keep that in mind. All right, next page real quick. Number 5. When we now go to try and define what our u and dv are, the general rule that I gave you earlier is that u, we probably want to be whatever has a derivative that will eventually terminate. Well, if we look at this, neither one of those is going to terminate. So e to the x's derivative will never end. The derivative of cosine, that would never end. It's an endless cycle for both. What that would mean is it doesn't necessarily matter which one you're going to let be your u. I'm going to let it be e to the x. So just so we all kind of look the same and these steps all look the same, let u be e to the x. That would then mean we're going to let our dv be the cosine of x dx. We know we need the derivative of u, so we can go ahead and get that done real quick. And we need the antiderivative of v. All right, so from there, you're going to do the antiderivative of e to the x cosine of x dx equals uv. So hopefully we're getting our pattern down at least, minus the integral of v du. So that would be e to the x sine of x dx. As we look at that, we just did one similar to this. We hopefully can recognize when we look at this integral here, this is not one that we know the antiderivative of, so we've got to set up another one. So just like in the previous problem, here it does matter when we do this type of a question. If in this original setup, you let u be the exponential function, then if we're going to have to do this a number of times, you have to let your u be the same exact u that you started with. If not, then things will get screwed up a little bit. So between the e to the x and the sine of x, make sure your u is e to the x. Our dv then would have to be sine of x dx. Take the derivatives of your u, the antiderivative of v. That's a negative cosine for you guys in the room, sorry. Should just pull this up. And then now let's plug in, see what we have. Because last time after the second one, we were good to go. So let's see now after the second one here if we're good to go. So now we're going to have minus. And then you have your integral. So now definitely put a bracket so this negative gets distributed to everything. So we're going to have uv. So that's now a negative e to the x cosine of x. Minus the integral of v du. So v du. So we're going to do negative cosine times e to the x. So this will be a negative e to the x cosine of x, and then our dx. A mess of negative signs there. So as we now go to try to clean this up, let's clean that up a little bit. So we have a double negative here, so this will become plus e to the x cosine of x. And then initially, what I'm going to look at here, I'm going to take this negative and a negative, so that's going to become a positive. But we still have the negative that's out in front of that, so we really have a product of three different negatives. So this is going to remain a negative integral of e to the x cosine of x dx. So now doing this 2 times, did we create right here something that we now know the antiderivative of? No. Do we have a function, either e to the x or cosine of x, that would eventually go away? Would this cycle ever end right now? No, you're going to continue to do this over and over and over again, unless you're very clever and you recognize something right now, because the answer is like one step away. So anybody feeling clever and notice something? Yeah, Andrew, I saw your hand go up first. What do you think? Because isn't this the same as the original problem that we are trying to solve? So he is saying, let's move this guy over to the other side by just adding it to the other side. If I added that to the other side, good, Andrew. Andrew's clever. That would give us 2 of these integrals. So then on the right-hand side, we have the 2 non-integral terms. So get to this step. Think about what we were trying to solve for, right? The answer to this question is the antiderivative of e to the x cosine of x. So can't I now isolate this e to the x cosine of x by just dividing everything by 2? So the answer to this question then is e to the x cosine of x, and then all of that divided by 2. I'm going to cheat just so we save a little bit of time. Just divide those by 2. Let's do it that way. Probably quicker and easier. Which then means over here, we're going to divide this by 2. And then just remember, even though we didn't have to do the antiderivative of that, we should have that plus either. Okay. So that's kind of tricky business there. That's not easy. Okay. All right, last couple. So now, I like integration by parts. You certainly need to use integration by parts. If you flip your quiz review over right now, so if you look at your quiz review, flip that piece of paper around, you're going to see me using integration by parts very little, right? See a bunch of arrows getting drawn. So integration by parts, I like it a lot. You need to know how to do it, because if you have a natural log involved, it almost always requires you to do integration by parts. But there is an alternative to this, and it's called tabular integration. So look at this problem right here. We've already done this problem, right? We did this problem on the first page, so we know what this antiderivative is. It should be something we should be able to do. But this is the first one where I needed you to do the integration by parts 2 times. Go to this one. What if I gave you x cubed? That's going to require us to do it 3 times. And ideally, we don't want to have to do it 2, 3, 4 times. And God forbid I give you an x to the 5th or an x to the 4th, right? So here's how we can do this instead. And it's called tabular integration. So take the 2 different parts of this integral. So you have e to the x. So whichever one has a derivative that would ever end, that's what we're going to start with. And on the left side of your table, you're just going to hammer out derivatives until you get to 0, until it has no more derivatives to go to. On the other side of the equation, you're going to do the antiderivative of the other part of that integral. So whatever this function is, it's e to the x. Just do your antiderivative. And you just continue to do antiderivatives until you have the same number of derivatives on the left side as you do integrals on the right-hand side. Then notice the arrows. The x squared gets paired with e to the x. So here, does it show this here below? No, it doesn't. So now, here's how we can now write this answer, and then we'll compare that to the one that we did. So take e to the x and x squared, you're going to multiply them together. That's our first product. Notice what our first sign is. You're going to keep the positive sign. So that would give us x squared e to the x. Our second product would be 2x and e to the x. So then do 2x e to the x. But notice what the second sign is. It's a minus sign. So whatever product would have occurred naturally between 2x and e to the x, you would want the opposite of that. So since that normally would have been positive, we would want that to be negative. Our third product is between 2 and e to the x. So you're going to do a 2 e to the x. Notice what your third sign is. It's a positive sign. So whatever the naturally occurring product would have produced, you're going to keep that sign. So in this case, this remains a plus. Add your constant. Same answer we got if you went back and looked at number 4. All right. Most people, as soon as they see this and they do 1 or 2, everybody goes to this. Now, there's certain ways we can test you, like number 5 above, hard to do it with this method. Any natural log problem, hard to do it with the table. All right. But that's how we can do this, make this. Oh, here it is right here. Sorry, I didn't move my paper down long enough. But that's the answer that we got earlier. So now let's jump to, since we're running a little short on time. Yeah, we'll do X. We'll do this one. This is pretty quick. And then you have the homework or the review that you can look at. So we could do this, but it's going to require us to do 2 integration by parts. So what we want is we want the derivative of the term that would have been our u. So in this case, we would, if we had done integration by parts, we would have wanted our u to be x squared. So that's the left-hand side. So we start with x squared, and you just crank out derivatives until you can't anymore. On the right-hand side, you're going to do the antiderivative of whatever your dv would have been. Well, we would have picked dv to be sine of x. So we start with that, and then just do antiderivatives until we get to the equal number of them. So the antiderivative of sine would be a negative cosine. Antiderivative of negative cosine is a negative sine. Antiderivative of negative sine is cosine. Then down the middle, we're going to go always start with positive, negative, positive, negative. We then multiply x squared times a negative cosine of x. So let me create some space up here. I don't know why that just moved. I don't understand why that whole thing just moved. Okay, so what oh man, now this visual is awful. I'm afraid to hit back because I'm afraid it's going to screw it up. Is there any undo button on Canvy? Anybody know Canvy well? There it is, there it is, there it is. Nothing's happening. There we go. There we go. What? I'm going to lose my mind. All right, let's just do it below. So our answer should be x squared times a negative cosine. So that's going to be a negative x squared cosine. And since the first sign was a positive sign, that just means you keep the naturally occurring sign. So since it was negative, you leave it negative. The next product would have been this 2x and a negative sine of x. So we initially would have a negative 2x sine of x. But since the second sign is this minus sign, that means we would want the opposite sign of what we normally would have gotten. So that's a positive. And then our last one would be the 2 cosine of x. And since we have a positive sign for our third sign, we keep the naturally occurring product, which is a plus. And then we add our c. That's our final answer. Sorry we didn't get through 7. However, I'm glad now I showed all the work in the review. So when you look at that review, you're going to see a lot of those. And I think hopefully after you look at that, people usually pick up this pretty quickly. When we do the tabular, most people really like the tabular integration. They think it's pretty straightforward. The only thing to look at for the review, and that's why the first 10 minutes of class tomorrow or so, totally fine going over some of those. You're going to look at the review. Think of it as an extension of the notes. There are limits on those. So it's just now, once you've done the antiderivative, we still got to go with the upper minus the lower, and then whatever that evaluates to be is going to be your final answer. Okay? So this is the only thing on your quiz tomorrow are these problems. If you know the notes and you know the review, I'm not going to try to do anything tricky. They'll all be similar to those questions. Yeah, Steve? You have to do the parts with that, and the other place where you're going to almost certain, you don't have to, but you have to be really, really good to understand how it would work, is if you have a natural log involved. It's also hard to do the tabular integration with a natural log. But every other part, usually it's the best way to go. Okay? Okay, we'll see you guys. All right. See you at home. Have a good day. Yeah, go ahead.